Hello everyone. So in this lecture we are going to start a new topic and we are going to move toward turbulence. And before moving to the turbulence, I want to talk about the concept of mean and the average, because that's being used a lot in turbulence studies. Because the flow is very turbulent, and we typically do these averages to have a better kind of understanding of the flow. So again, the turbulence occurs at high Reynolds number. And when we have turbulence, the flow will fluctuate a lot and it can be chaotic. So now we use these statistical methods like just taking averages to kind of simplify the analysis and understanding of the flow and understanding the mean flow. So we divide the flow into a mean and also a fluctuating part. Okay, so we show the mean either with a capital letter like X, or we show it with these brackets, bracket X, or with just a bar. Okay, so these are the three ways that we show the mean variable or the average. So when we take the average, again, this is defined from your simple statistics course. So 1 over n, the number of kind of data that we have, then sigma I equals to 1 to n of that data, xi. Xi can be anything, can be velocity, temperature, or any variable, okay? So we have different type of averaging. So we can have a temporal averaging or time averaging. So that's something we know. So time averaging or time average applies at one specific point in space over a period of time. So what you actually do, you take a specific point in space and then take this average in time. So these will be different realizations in time for just one specific location, okay? So let's look at some example. So here, say we have two types of flows. So first we have a pipe flow. So this is a pipe flow. The first one, I have like a laminar steady flow. So my profile, the wind profile or the water profile in this pipe is going to be like this. It's a laminar flow, okay? And then in the second example, I show a turbulent steady flow, okay, rather than a laminar. I want to show how a turbulent flow looks like. So turbulent steady flow. So we can have something like this because it's a turbulent. This is actually how it looks like. The flow, the velocity profile. Okay. So now when we want to do time average, okay, say we put a sensor somewhere here at this location, a fixed location in this pipe, similar thing here. So we have a sensor. We put it in a fixed position in space. So let's first look at the laminar flow. So here we put the sensor like this. Let me just put it like this. To measure, say, wind or the flow, the water flow. And how does this look like when we have a steady flow? So when we have a steady flow, a laminar flow, if we want to plot the U here as a function of time, so this is time, t, and here we have the velocity at that sensor here, that we sense it here. So for a laminar flow, the velocity will be always constant. We have no variations in the velocity. Okay? In time. No variation in velocity in time. We might have some variation in space, like if you go higher, the velocity might increase in the center of the pipe. Okay, so now let's look like how the velocity will change if we measure it in a turbulent flow. So in a turbulent flow, we are going to have a lot of fluctuations. So it might look like this. Okay, so this is turbulent. Now, we can take the time average for this specific location in space. And if we take the time average, it will look like something like this. Okay, and this is going to be actually U, capital U, or U bar, or you can show it with this bracket. And this is actually the time average quantity here. Time average. Okay. So this was for time averaging when you have just one fixed point in the space, like here or anywhere, and then you take so many measurements and then you take the average in time for that signal. We can have also spatial averaging. So this was temporal averaging. We can also define spatial averaging. So spatial average applies at some instant in time over spatial domain. So what does this mean is that for a spatial averaging, you take snapshot of the flow in one time, one snapshot, and then take a spatial average in one direction or in multiple directions. So say you have a realization for a flow field, say at one point for a spatial domain, okay? So the velocities could be like this, okay? And then you take the average of these either, for example, in the x direction or in the y direction or in all directions, okay? So this will be like, again, spatial averaging. So you take one snapshot of the flow and then take the average, okay? We can also have another concept which we call ensemble average. So ensemble average consists of the sum over n identical experiments. So what does this mean is that you take, like, you do an experiment n times, the same experiment, and then you take the average of all your results for those n identical experiments. And that's called ensemble averaging. So when we talk about ensemble averaging, and that's what we usually do in turbulence studies, that means just taking over, averaging over n identical experiments, okay? So the other thing, what we do is we typically, because understanding the mean flow and averages are easier than the fluctuating part, because the fluctuations, as you see, can become very chaotic. So we typically, in these turbulence studies, we divide and split any signal, any turbulent signal, like velocity signal or like temperature, anything, or fluxes, into a mean part and a turbulent part. So if you have a velocity signal, an instantaneous velocity signal, like u, and we show it with u, we split it to a mean part plus a fluctuating part u prime. And we write it like this. So this will be instantaneous this is the mean part, and this would be the turbulent part. So as you see here, the signal is this u bar, this time average, plus all these fluctuations, right? U prime. So we call all those fluctuations as U prime. Okay. So now what I want to do, I take the average. So take average of the above expression, the above expression. So if we take the average, take average of that. So we can show it this bracket. So bracket u or u bar equals to bracket u plus u prime, the average of this. So again, the averaging is just this sigma, and you can take sigma. You have this linearity of the sigma, so you can actually separate this out. These two variables, you can separate them, because again, these are sigma x plus y, and you can write this sigma x plus sigma y, right? So we have this. These are just sums. So I can write this as bracket u plus bracket u prime. Okay, and we know the average of the average is going to be what? Is going to be itself, the average. So again, this, what is this? The average of the average. The average of the average is just one number, right? It will be one number. And if you again take the average of that, it's not going to change. So it's going to be the same thing. So this actually equals to itself, u bar. So u bar is just u bar. And the bracket of u, capital U, is going to be again u, capital U. Okay? So this equals to capital U plus U prime. Again, because this is just one number, and when you take the average, it's going to be equal to this. And what is this? This is just the average of U. Right? This is just a definition, the average of U. So this equals to average of U plus average of U prime. So interestingly, these two are going to cancel out from both sides. And what we get is that the average of the fluctuations, or the turbulent part, is always going to be 0 if you have an ensemble average, so like this. Enough averaging. So actually here, if you have a lot of data and then take the average of these fluctuation parts, the average of those fluctuations, this means is going to be 0. Sometimes they are positive, U prime is sometimes is positive, sometimes they are negative, but when you sum them all and then take the average, they will become 0. Okay. So the second thing that I want to calculate is the average of U square. What is going to be the average of U square? So the average of U square, I can write it as the average of U, capital U, plus U prime squared, which is going to be the average of capital U square plus 2U U prime plus U prime square. And again, I can write these in different terms. I can just write it as average of U square, capital U square plus the average of, I can take 2 out, of U prime plus the average of U prime squared. And again, this is going to be what? Is going to be capital U square, because this is again U bar is just a number. And here I can write this as, I can take U out because this is just a number. Capital U is just a number, so this equals to 2U times the average of U prime plus the average of U prime squared. Okay. Again, this is because the average of average is just average. Okay. So what is this going to be? What is this? From here, you see that it's just 0. You know that the average of fluctuations is 0. Again here, if you have these fluctuations, their average is going to be 0, okay? So this term is going to be just 0. And so this will equal to, we get that the average of u square is going to be capital U square plus the average of u prime square. Okay. So this is another relation that we can find by this definition. Okay. So now, based on these definitions, I define Reynolds decomposition. So the Reynolds decomposition is actually uses a similar concept. So in the Reynolds decomposition, we decompose every signal into a mean part and its fluctuating part. So for example, for velocity, as we said, ui equals to, in any direction, capital Ui plus its fluctuating part, u prime I. Similarly, for pressure, we can write this. So we have capital P plus P prime. Even for stresses, you can have that tau ij equals to Tij plus tau ij prime. So this is called Reynolds decomposition. Okay, so now I want to mention some rules for these averaging, because we are going to use them to find Reynolds average equations. So the first rule is that the average of any fluctuating variable, any prime, is 0. And we prove this here for u prime, right? The average of u prime is 0. And this is a general rule for any variable. The average of the fluctuating part of any fluctuating part of any variable is going to be 0. The second rule that we have is that the average of any average variable is just the average variable. And we showed it here. We used it here. And here, the average of the average variable is just that average variable. Okay, so this is another rule that we have. The other rule is when you have the multiplication of an average variable and a fluctuating part, and then take the average of this equals to, because the average is just, you can take it out, it's just a number from the average, is going to be the average quantity times the average of the fluctuating part. And we know this part is 0, so this is just going to be 0. And we used it here. So this is a general rule for this. And the other rule that we have is that although this is 0, the average of two primes or two fluctuating variables that are multiplied by each other are not necessarily 0. So for example here, this is not necessarily 0. U prime square, if you take the average of that, it's not necessarily 0. Okay? Again, because these are going to be always a positive number, unlike here that can have positive and negatives. if you have like a square of that, or even if they are not even squared, if there are two different variables that can be like u prime and v prime, again, if you take the average of that, it's not necessarily 0, okay? So this is another rule, and the other rule that we use is that the average of derivative of a variable equals to the derivative of the average variable. In other words, we can take the average, the sigma, inside the derivative, right? This is a sigma. This is like sigma x equals to partial x of that sigma, okay? So this is another rule that we are going to use in order to derive the Reynolds averaged quantities, okay? So now let me use this. So first I want to use this and apply this Reynolds decomposition and these rules into continuity equation. And in the next session, I'm going to apply these to the Navier-Stokes equation. So Reynolds averaged continuity equation, okay? So the continuity equation in differential form was d rho over dt plus rho partial ui over partial xi equals to 0. And in incompressible flows, in incompressible flows, we knew that the divergence of velocity is going to be 0, or partial ui over partial xi is 0. Okay, so this is the continuity in incompressible flows. So, or partial ui over partial xi equals to 0. So let's apply Reynolds averaging into incompressible flows. So for the velocity signal, I can write it as u, capital U plus u prime. So partial over partial xi of capital U plus u prime I equals to 0. So we can, this is again, we can write this as partial over partial xi of u, capital U, plus partial u prime I over partial xi equals to 0. Okay. Now I take the average here, so take average of this, the whole equation. So what we are going to have is the average of partial u over partial xi plus the average of partial u prime I over partial xi equals to 0. So this gives me, I can use this rule here and take the average inside the derivative. So I have partial, the average of u over partial xi plus partial u prime I over partial xi equals to 0. And we know from here that this is just 0. And we know that this is just going to be u, capital U. So this means that partial capital U over partial xi equals to 0. interesting. So this means that the continuity in incompressible flow becomes partial capital U over partial xi equals to 0. But even more interesting than this, we can put this here into this equation. And if you put it there, what we are going to get? This means that this term is 0, and thus this term has to be 0 as well. So partial u prime I over partial xi equals to 0. So the incompressible flow, the Reynolds average, in incompressible flow, the Reynolds average continuity will be reduced to these two equations. One is for the mean flow, the average of the mean flow, the divergence of the mean velocity is going to be 0 always in incompressible flow, and also the divergence of the turbulent velocity, u prime I, is going to be always 0. Okay, so in the next session, I'm going to drive the Reynolds average Navier-Stokes equation. So we are going to apply these Reynolds decomposition to Navier-Stokes and take and get the Reynolds average Navier-Stokes or Rance equation.